Hi everyone, my name is Yahui, and for my final project, I choose to study on optimizing performance and security in Intel SGX applications through multi-threading and switchless calls. Here is my presentation outlines. First, we are going to go over some background information, including software privilege level, trusted execution environment, and its evolution. Then we're going to deep dive into some SGX concepts, including Enclave, Enclave page cache, and Enclave page cache table. Also, we're going to go over some concepts including thread control structures and multi-threading concurrency in SGX. Then we're going to move on to my project demonstration. We are going to go over some problem statements and my setup environment. Also, we're going to show the architecture design of the project and a demo. Then we're going to evaluate my project and do a security analysis of my project. To start with, software privilege levels restrict the access control. System management mode is a highly privileged execution mode used for hardware and power management. It provides low levels control for BIOS or firmware to manage system hardware, isolated from other execution modes to maintain system security and stability. VMX root is a privileged mode of operation for hypervisors in Intel virtualization technology. It provides hypervisor direct access to manage and control virtual machines. VMX non-root mode is less privileged mode for guest operating system running in virtual machines, which isolated from the hypervisor. It only has restricted access to hardware and relies on hypervisor, sometimes for certain operations. The traditional x86 architecture uses protection ring, which is a hierarchical protection domains to provide different levels of access to resources. Ring 0 here is the most privileged level, and it is used by kernel mode of operating system. It has fully access to hardware and system resources. Ring 3 is the least privileged level and has limited access. It is often used by user mode applications. It relies on system calls to request privileged operations. Our SGX Enclave lays in this category. Ring 1 and Ring 2 is rarely used and is often reserved for special purpose like device drivers. Trusted execution environment is defined as a tamper-resistant processing environment that runs on separation kernel. It guarantees the authenticity of the executed code, the integrity of runtime states, and the code confidentiality. It has four main secure prerequisites. First is data separation. Data within one partition cannot be read or modified by other partitions. Also, it has sanitization. Its shared resources cannot be used to leak information into other partitions. Control of information flow means the communication between partitions cannot occur unless specifically permitted. It also has fault isolation, means when there is a security breach in one partition, it cannot be spread to other partitions. And the secure boot of TEE architecture is established by a chain of trust. The chain of trust is established through multi-string design, with initial code protected by a tamper-evident hardware model. And this is happening inside the security boot. It ensures that only authorized code is loaded during the boot up by checking the integrity of the code using some cryptographic hashes. Then it will go to secure scheduling. It balances and coordinates TE tasks with the main OS to maintain responsive without compromising the real-time performance. it has a real-time constraints always. Then we have inter-environment communication. It is an interface for communication between the TE and the rest of the system, which should be reliable, have minimum overhead, and protect communication structures. It faces challenges like message overload attacks, data corruption, memory flaws, and unbound weights. And inside the trusted kernel, we have secure storage, which is only allowed access by secure entities. It's commonly implemented through sealed storage, which consists of an integrity-protected secret key, cryptographic mechanisms, and data rollback protection mechanisms. Then we have Trust IO Path, which is a safeguard to against protect attack against peripherals like screen capturing, key logging, overlying, or phishing. TE evolves over the years, and here are highlights of Intel SGX improvements over the previous approaches. So first, we have Trusted Platform Module. It's a method for secure boot that measures the software stack and generates an attestation report. However, it has limitations, such as only occurring during boot and will rely on the BIOS, TPM chip, and the CPU package as the trusted computing base. Then we have Intel Trusted Execution Technology. Intel is trying to improve TPM by allowing late launch is enabling software to be measured after boot completion. However, it has its own drawbacks, such as taking over the entire system during the measured code execution and still rely on the TPM chip and CPU package for the TCB. Then we have Intel Software Guard Extension. It is an enhancement of TXT that allows application logic to run in a secure and opaque manner without being tampered by external software or hardwares. Enclaves are more dynamic and flexible than TXT, allowing multiple enclaves to run simultaneously and interact with untrusted portions of the application and operating system. This approach reduced TCB to only the CPU package, eliminating the need for TPM and BIOS involvement. SGX features an alternative, non-hierarchical protection model for isolated application compartments called enclaves. To start with, it has processor reserved memory, which is used to create enclave for storing sensitive data for executing critical operations. It ensures that the process can execute its tasks without interfering other process. By isolating the memory space for each process, the system can provide unauthorized access, data corruption, or performance issue. The SGX is implemented through a new type of memory called enclave page cache that is carved by the BIOS at the host boot time. EPC is treated specially by the CPU as there is a memory encryption engine to ensure that all the data go to and from the PC are encrypted. This prevented hardware-based attacks such as bus snooping. The attackers can steal secret by tapping the memory controller or the memory bus, as this region of memory is not accessible to any software when CPU is not running in enclave mode. EPC is guaranteed by hardware, and enclave can only access its own page. This memory, despite being protected, is still managed by OS and hypervisor, which does the allocation memories to process address spaces, handling invocations, and does so in a way that it doesn't compromise confidentiality and integrity of any of the secrets. The enclave page cache map is a hardware-managed mechanism that monitors the status of each enclave page cache. It stores management-related information for the corresponding EPC, such as valid-invalid status, read-read execute permissions, page tabs, and the virtual address range through which the EPC can be accessed. By employing EPCM, an additional layer of security is provided and compared to the traditional paging and segmentation method, as it does not rely on trustworthiness of the operating system. This hardware-based approach ensures that the EPCM is not directly visible to software, hence improving the overall security of the enclave memories. And here is a simple SGX application overview. So for any applications of SGX, it is always divided into trusted and untrusted part. Trusted part encapsulated the sensitive operations and data in an enclave, while the untrusted part handles the general application logic, interacts with external components, and communicates with enclave. Also, it does not have direct access to enclave. And here is a simple workflow of an SGX applications. So the applications start with creating the enclave, and the enclave is loaded inside the enclave page cache. Then the application establishes a secure communication channel with the enclave. It typically uses remote attestation. Remote attestation allows the application to verify the integrity and identity of the enclave and ensure that it is running the expected code. A shared secret key may be generated and exchanged during this process to encrypt and decrypt data securely. Then it will perform secure operations. The applications can make calls to enclave trusted functions, also as e-calls, passing any necessary data as input, and the enclave will process the data securely and return the result to the application. The data passed between the enclave and the application may be encrypted using the previous exchanged secret key to maintain confidentiality. At the end, it will terminate the enclave. The application will destroy the enclave and release the reserved memory to ensure that any sensitive data within the enclave is properly cleaned up, and the application will process the result returned from the enclave, taking any necessary actions based on the secure computation performed within the enclave. And here are some real-life applications using SGX. So first, SGX can be used to protect sensitive code and data within unmodified Windows application. It creates a secure execution environment that isolates the application from the potential threats without requiring modification of existing application code. SGX can also be used to enhance the security of distributed data processing frameworks like MapReduce by ensuring that sensitive data and computation are securely executed within the enclaves, preventing unauthorized access or tampering during the data process stage, and maintaining the data privacy even in untrusted environments. Also, SGX can be employed to create secure Linux containers, which will provide an additional layer of security to containerize application by isolating sensitive code and data within the enclaves. It will safeguard against attacks targeting the container infrastructure or other components in the shared environment. And now we come to thread control structure in SGX. A thread in SGX enclaves can be used to execute parallel tasks within the secure environment, taking the advantage of multi-core processors to improve performance. EPC provides a secure memory region where the thread's data, code, state are stored and protected. Here are some key elements for a thread. While the use of threads within Enclave, when multiple threads are created within Enclave, each one of them has associated thread control structure and memory allocated from the EPC for its stack and heap. The CPU ensures that the threads only access the memory pages within the EPC, protecting the confidentiality and integrity of the Enclave data. While the use of thread within Enclave offers performance benefits, there are still some downsides. First of all is the limited EPC size. When the EPC becomes full, some pages must be evicted to make room for new pages. When a thread accesses a memory page that is not currently in the EPC, a page fault occurs, leading to performance overhead. In a multi-threaded environment, contentions for EPC space can be further worsened due to this issue. Also, we have synchronized overhead. When multiple threads access shared data within the Enclave, the synchronization mechanisms must be employed to secure data consistencies. These mechanisms can introduce performance overhead, especially in case of high contention of shared resources. Also, it introduces some security concerns. We will discuss about this later. So for this project, we want to resolve two things or three things. First of all is the context switching overhead. The traditional host-enclave interaction involves frequent context switching between the host and the enclave, which adds a significant performance overhead due to the need of save and restore CPU state during each transitions. Also, the synchronization and communication, as the threads may need to communicate with each other, which can introduce additional overhead, primitives, and inter-thread communication mechanisms. And also due to the Enclave page cache has a limited size, which affects the number of concurrently running threads in an enclave. As the number of threads increases, the memory management overhead and potential EPC contentions can lead to performance bottlenecks, impacting the overall system efficiencies. So the goal of this project has two main targets. First of all, we want to minimize the context switching overhead. So one of the primary goals is to reduce the performance overhead associated with frequent context switching between the host and enclave, enabling more efficient communication and faster executions of enclave functions. Then we want to improve the resource utilization and parallelism. By employing switchless calls, the host calling thread can continue executing other tasks while the enclave worker thread process the request functions. This approach will allow better resources utilization and increase parallelism, leading to improved performance and reduced latency. So for our evaluation method, we decided to perform 100K switchless on-calls and 100K switchless e-calls. We use the time of those comparing to the regular calls and see how it will enhance the performance. For my experiment setup, I am using an Ubuntu 20 Linux server, and for my server, it is Intel Xeon. And here is our switchless design architecture. We have the untrusted part, which is the host, and we have the trusted part, which is the enclave. Like any other host or enclave does, inside the host, we first initialize the enclave, and we will make regular or switchless calls, e-calls more specifically. We will measure the execution times, and then we will terminate the enclaves. So to modify to switchless, we have two threads. One is called calling thread, relies inside the host. This calling thread will continuously make switchless calls. It will prepare the input data for the enclave function and place it into the shared memory buffer. It then posts a request to enclave worker thread, providing information about the enclave function to be executed and the location of the input data in the shared memory buffer. Once the request is posted, the calling thread can continue executing other tasks without waiting for enclave worker thread to complete the request operations. And for the worker thread, we have it relies inside the enclave. The worker thread will continuously monitor and serving the switchless call. It will monitor the shared memory buffer for incoming requests from the calling thread. Upon detecting a new request, the worker thread retrieves the input data from the shared memory buffer and processes the request enclave function. After processing the enclave function, the worker thread writes the result back to the shared memory buffer and mark the request as complete. And here is how we're gonna deal with synchronization and communication. We use a memory shared buffer. This memory buffer acts as a communication channel between the calling and the worker threads, allowing them to pass data and the function request. To ensure proper synchronization and prevent data races, the shared memory buffer implementations using the synchronization primitives using atomic operations. Here is my experiment demo. To set up the switchless enclave environment, we first create one thread for enclave worker, and then to create the switchless enclave, we first declare the structure address and the setting type. And then the first thing we want to test is the host eCall to enclave add in regular to transition into enclave to compute a summation of two random integers. And inside this regular function here, it will get called host increment regular, which is a regular function called by the enclave, and this requires context switching between the host and enclave. We time the execution time and move forward for calling the switchless enclave call. And inside the switchless, it's the same computation, but instead of doing a regular call, we call switchless increment, which allows the calling thread to continue executing other tasks without waiting for the host function to complete. And then to measure the switchless eCall performance, the host will then measure the time taken to make n calls to enclave decrement switchless function, which is here. We measure the performance time and compare it against the time take to make n calls for regular functions. And to run this, we will use CMake to build this project. And then we CMake. Wow, it's running. And then to run the project, we run make run. And this will output how long the execution time for different scenarios. And this is our experiment. The result shows a significant performance advantage using switchless calls over regular calls for both host-to-enclave and enclave-to-host interactions. The switchless on-call are approximately 4.9 times faster than the regular on-calls, and the switchless e-calls are approximately 5.1 times faster than the regular e-calls. To summarize, the switchless calls offer significant performance improvement over regular calls, making them more efficient for scenarios where the frequent calls between the host and enclave are required. The reduced latency and overhead in switchless call lead to a more responsive and faster system. Here are more results I got from optimizing the number of host workers and enclave workers. I was hoping to see some trends like by increasing the number of workers, the execution time will decrease. It is evident that there is no clear optimal configuration that stands out. This lack of definitive observation can be attributed to multiple factors, including the nature of the workload, the application design, and the threat contention. The optimal options seems to be the configuration with 1 host worker and 27 enclave workers, but with the enclave page cache used for creating these 27 threads, I don't think it's worth to do it. So, for my application scenario, it is optimal to have 1 host worker and 1 enclave worker. And now we come to the security analyst part. We want to see whether switchless call help to mitigate the flood attack. So when multi-thread concurrency helps improving performance and utilize available hardware resources more efficiently, flood attack is one of the more common threats. The relationship between multi-thread concurrency and flood attacks lies in how the enclave manages its resources, specifically the thread control structures and the input page cache memory. When multiple threads are running concurrently within an enclave, these threads are shared among these resources are shared among threads. During a flood attack, attackers create an excessive number of concurrent threads, attempting to consume all available thread control structures and enclave page memory resources. This can lead to resource starvation for legit threads, preventing them from executing correctly or causing significant performance degradation. Switchless call efficiently manage of worker threads and shared memory buffer used for communication between enclave and host. When switchless calls are used, a fixed number of worker threads are created to handle the on-call and e-call. This control allocation of worker threads can help minimize resources contention and help overall improvements by limiting the number of worker threads and ensuring that properly managed, the impact of flood attack can be reduced. In this project, several challenges were faced, including comprehending the intricate interplay between thread enclaves and enclave page cache within SGX and how they influence multi-threading and scheduling approaches. Additionally, implementing the concept of switchless on-call and switchless a-call present its own set of difficulties. Another threat was designing an optimal number of worker threads for a system with a specific number of cores, ensuring the maximum performance and efficiency, while taking into account the complexity of the switchless model. In this project, we explored an Intel software guard extension technology focusing on multi-threading and switchless calls. We investigated the interaction between enclaves, threads, and Enclave page cache, as well as the complexity of thread scheduling and potential security risks, such as flood attacks. We implemented Switchless on-call and Switchless e-call, optimizing the number of worker threads for systems with a specific number of cores to achieve maximum performance. We also analyzed the security implications of switchless calls and their potential impact on reducing flood attacks. The project aimed to understand and adjust the challenges associated with Enclave multi-thread